Hey students, welcome back. So in this one I want to show you how the second law, which is force equals mass times acceleration, can be used to solve for the velocity of a satellite. So in space you have, say this is the sun, the earth revolves around it, or say this is the earth, a satellite goes around it. Well, you need to know the velocity of a satellite. So for example, if we have the earth right here, sorry about that. Getting a little bit sticky on me there for a second. All right, let's see. Here we go. All right. So if we have the Earth right here, right, and you have a satellite moving around it. There's my satellite. Woo. Okay, the satellite is moving around it. The satellite has to have a certain velocity, right? Because the Earth is pulling it down towards its center. So its velocity to the side is going to cause it to be pulled, and it has to have the correct velocity so that it continues to fall around the Earth. So if it has the correct velocity, it will fall at the same rate it's being pulled toward the center of the Earth. And if it does that, it keeps going around and around and around. And this is also the idea of weightlessness. So if you ever see the astronauts and they're floating around in the space station, is it because there's no gravity up there? It's actually not the case. There's plenty of gravity up there in space where they are, but the whole deal is they're actually falling down with the acceleration of gravity. So gravity isn't affected. You don't see the effects of gravity on them because they're basically just going with it. But they just continue to fall around and around and around. So it looks like they're floating around, but they're actually in a constant perpetual state of free fall. All right. So let's look at how would we derive the velocity of a satellite from force equals mass times acceleration? Well, we remember that Newton said that force, the gravitational force equals g times the mass of the satellite times the mass of the central body divided by the distance between them squared, right? So what are we saying by that? Well, if this is the gravitational force, or this is the centripetal force, the force of centripetal, we're also saying that equals mass times acceleration, right? So we're saying that the gravitational constant equals the mass times the acceleration, because that's the other part of this force equals. Or you could say mass times the acceleration of centripetal here, right? And the acceleration of centripetal is what? It is the little g. So this right here, this acceleration of centripetal, when we talk about g as equaling 9.8 meters per second, that's what that is. All right. All right. So that means that little g, which we have always known as 9.8 meters per second squared, is really just also this right here. It is the acceleration of centripetal in terms of this formula right here. So that'll come into play in a little bit. But let's get to solving for velocity. So if you look right here, we have already derived out that the force of centripetal equals the mass of, let's put this is the mass of the satellite times the velocity squared divided by the radius, right? And we also know that equals then the force here, because this is the force of centripetal, or and this F right here are essentially the same thing. So that equals that. So let's go ahead and set those equal to each other. So we have the mass of the satellite times the velocity squared divided by the radius equals g times the mass of the satellite times the mass of the central body divided by the radius squared. So these two are equivalent. They equal each other. So we can set them in this fashion. Now let's go ahead and arrange, because as you can see within this equation, we have velocity. So all we have to do is rearrange this. So let's go ahead and come over here and let's divide or multiply by the, see, we're dividing by the radius over here, so I'm going to multiply by the radius over here, and that's going to get rid of that on this side. And then over here we also have the mass of the satellite up here, so I'm going to divide by it on that side, and that's going to get rid of that right here. So let's see what we have left. We have velocity squared equals g times the mass of the central body times we've got the radius on top, and so that gets rid of one of those, so we still have the radius on the bottom. So velocity squared equals the gravitational constant times the mass of the central body divided by r. So now all we have to do is take the square root of that. So here's where we end up. Velocity of the satellite equals the square root of the gravitational constant times the mass of the central body divided by the radius of that satellite, right? So how far away it is from the center of the central body. So there we go. So that is then the equation that we use to solve for the velocity of a satellite. So last time we derived the period of a satellite. Now we derived the velocity of a satellite. So once again, if you drag all this back, you realize that this equaling this, right, came out of this, right, which equals this. So essentially all of this right here, this is from this, derived out of this. So essentially this is Newton's second law, force equals mass times acceleration. They're all related in this thing. So what we're going to do in the next one is I'm going to quickly show you then how can you use force equals mass times acceleration to derive the actual gravitational field equation to solve for a gravitational field.